matrices that already contain a certain rotation about the x, y, or z axis, and also methods for rotating an existing matrix about the x, y, or z axis at a specified angle. In this example, we have an object representing a typical axis tripod. This object has a transformation equal to the identity matrix, with the x, y, and z local axis aligned to the world x, y, and z, and translation of 0. We can create a new matrix containing a rotation about the y-axis at 45 degrees by using the rotate y matrix constructor and passing the angle as a parameter, in this case 45 degrees. The result is a new matrix which contains the rotation about the y-axis and the x and z-axis appear to be the projections on the world axis with the typical values of sine and cosine of 45 degrees. We can do the same with the x and z. Note that in all these cases we are constructing a new matrix which replaces the existing transformation matrix and has an offset translation part in row 4 equal to 0, 0, 0. That means that if our object was placed somewhere else in the world, assigning one of those matrices is going to return it back to the origin. We are not incrementing the rotation, we are assigning a pre-rotated matrix that already contains the rotation and always has an offset of 0, 0, 0. If we would place our object at coordinates 0, 0, 1, 1 unit above the origin, we could try to rotate its existing transformation matrix about the y-axis at the angle of 45 degrees. In this case, we are transforming the existing transformation matrix by rotating it at 45 degrees in world space. That means we're rotating about the world y-axis and about the origin. This is the same as multiplying the existing transformation matrix by a rotate y matrix containing a rotation of 45 degrees. As you can see, the result is the same. This means that we take the existing transformation and transform it about the 0, 0, 0 origin specified by the translation of the rotate y matrix, and we rotate it about the world y specified by the matrix constructed by rotate y matrix. Obviously we can do the same with the x and the z world axis. It is also very important to note that the order of this transformation is significant. We cannot freely switch the order of the operands. In this case, we would create a new transformation matrix which contains a rotation about the y-axis, but the row 4 would be at 0, 0, 0, and then this rotation about the y-axis would be assigned to the object and transformed into the space defined by the object itself. Executing this is going to cause the object to be rotated in its local space about the y-axis. In addition, this rotation is incremental. That means evaluating it multiple times is going to take the existing transformation, apply the rotation, and then transform into the last transformation space. Thus, evaluating multiple times incrementally changes the rotation. The same applies to the case where we're rotating about the world coordinate system. Evaluating multiple times leads to incremental rotation about the world origin. It is important to note that if the object contains non-uniform scaling, using a local rotation could lead to a skewed transformation matrix where the three axes are not orthogonal to each other anymore. This is why non-uniform scaling is a very bad idea and shouldn't be used at object level at all.